because hydronium concentration is higher than hydroxide, that means the concentration is greater than 10 to the negative 7, means the pH is less than 7, right? 10 to the negative 5 is greater than 10 to the negative 7. The logarithm of 10 to the negative 5 is negative 5. The pH would be 5, less than 7. So the reason why the pH scale is turned upside down is because of the negative sign in front of the logarithm. As numbers get bigger, their logarithms get bigger, right? You put the negative sign in front, as numbers get bigger, their negative logarithms get smaller. That's why the pH scale is upside down. Why'd they turn it upside down? Well, why'd they put the negative sign in front? They put the negative sign in front because most of the time, almost all of the time, concentrations of hydronium ions are less than 1 mole per liter, which means their logarithms are negative. So if we simply took the logarithm and didn't change the sign, all our pHs would have to have a negative sign in front. And that's confusing. Then turning it upside down is confusing as well. But, you know, once you get used to it, it's okay. Right? How are we doing? If hydroxide concentration goes up and hydronium goes down, then the pH goes up, right? Hydronium concentration gets smaller, the logarithm gets smaller, but the negative of the logarithm gets bigger, right? How are we doing? Higher hydronium than hydroxide, pH is below 7. We describe that solution as being acidic. Higher hydroxide than hydronium, the pH is greater than 7, and we describe that solution as basic. We also use the word alkaline. Okay? Those are synonymous. Those are synonyms. And if we happen to have an equal hydronium and hydroxide concentration, we call that neutral. Pure water is neutral, but there can be other things dissolved in the water and still be a neutral solution, right? I can take a basic solution and I can add an acidic solution to it, and the hydronium ions will react with the excess hydroxide ions and neutralize them, and I can make the solution have the same hydronium and hydroxide ion concentrations. Yeah? Even though there'd be lots of stuff in there. The conjugate base of the ion that came with the hydroxide ion to make it basic. The conjugate base of the acid that I add. Those would all be in the solutions, even though the hydroniums and hydroxides would be equal. How we do it? So for instance, if I add a Arrhenius base, what key thing does an Arrhenius base contain? Hydroxide ions. If I add an Arrhenius base to water, sodium hydroxide, lithium hydroxide, potassium hydroxide, magnesium hydroxide, aluminum hydroxide, any of those things would dissolve and form hydroxide ions, right? And hydroxide concentration would go up, and pH would go up, wouldn't it? Right? Excuse me, I should have said, hydroxide would go up, hydronium would go down, pH would go up. Okay? Now, of course, if I add an Arrhenius acid, which is also exactly the same as a Bronsted-Lowry acid, then hydroniums are going to go up. Every Bronsted-Lowry acid, if it's stronger, if it's strong enough, is going to give hydrogen ions to water molecules that it's dissolved in, and increase the hydronium concentration, and the hydroxide will go down, and the pH will go down as well, right? How are we doing? Okay, so I add an acid, Arrhenius acid or Bronsted-Lowry acid, they're the same, aren't they? If the Arrhenius acid or Bronsted-Lowry acid is strong enough, we won't get into determining which is strong enough and which isn't. We know that the ones at the top, those 5 or 6 acids at the top, are strong enough, aren't they? Okay? If I add a strong acid to water, it's going to pass hydrogen ions on to water molecules and make hydronium ions, right? And hydronium concentration will go up, and the pH will go down. Right?
hydronium ions, and then hydroxide ions with a seesaw.
On the seesaw, right?
Okay. What about the K-test
The,
ions that
so, we're not really, don't know that I really want to. I don't want to do that right now, because it gets a little confusing. Where would the cutoff be? I think where you're going is, on our list of acids, right? Where would the cutoff be for an acid that would lower the pH of water if we added? Right? We know ammonia won't lower the pH if we add it. It'll increase the pH. We know perchloric acid at the top, and the other acids at the very top, will lower the pH if we add them to water. So is there a point at which an acid is added and it won't change the pH? The answer is yes, but I don't really want to go there right now. Okay? Now, what about a Bronsted-Lowry base? What if I add carbonate ion to water? First of all, is carbonate ion hydroxide ion? Carbonate ion hydroxide ion? No. Is carbonate ion hydronium ion? So how can it affect the pH if it's neither hydronium nor hydroxide? If I add carbonate ions to water, are you with me? Could they react with hydronium ions? And make what? HCO3 minus and water. Here's the point. What does a Bronsted-Lowry do? What does a Bronsted-Lowry base do? Takes hydrogen ions, right? And is carbonate ion a pretty good Bronsted-Lowry base?
Yes. Yeah.
It's down there, isn't it? It could take hydrogen ions away from H3O molecules, H3O plus ions, wouldn't it? Right? And all we have to do is look at the two bases that are competing. The base that has the hydrogen ion is water. The base that's trying to take it away, carbonate ion, who's stronger as a base? This one is. So this one's going to be pretty good at taking hydrogen ions away from hydronium ions. Here's the key, folks. If I add carbonate ions to water, what's going to happen to the hydronium ion concentration? It's going to go down. Carbonate ion is going to take hydrogen ions away from hydroniums and make the concentration go down. If the concentration of hydronium goes down, the concentration of hydroxide goes up, and the pH ends up being less than 7, doesn't it? I'm sorry, I said that wrong. Let's recover. Okay, let's back up. Let me start again, because I said that wrong. If I add carbonate ions to water, I take hydrogen ions away from hydroniums. Hydronium concentration goes down. pH goes up. Right? That's where I misspoke, and I wanted to make sure that you all didn't get that. Got it correct.
Well, wouldn't it also increase the OH ions because
Yes.
H?
Can't change this without changing that.
Well, yeah, but like, well, okay.
Yeah. One goes up, the other goes down, regardless of how we do that. If I make this go down, that goes up. In other words, adding carbonate ion to water, one of our strong bases, is like adding hydroxide ion to water, isn't it? Now the carbonate contains no hydroxide. Where's the hydroxide come from? It comes from this equilibrium that is constantly occurring in water. One goes down, the other goes up. Mathematically expressed like this. Okay? So a Bronsted-Lowry base, like carbonate ion, like sulfide ion, like ammonia, NH3, all of those are fairly strong Bronsted-Lowry bases. They affect the pH kind of indirectly. They take hydrogen ions away from hydroniums, and if they take hydronium ions away, the concentration of hydroniums goes down. concentration of hydroxides goes up, and we have our definition for a basic solution, don't we?
Wait.
No surprise. No surprise when I add sodium hydroxide that the solution becomes more basic, right? Because sodium hydroxide dissolves to form sodium ions and hydroxide ions, right? And how can we affect this balance by adding sodium hydroxide? We're increasing the hydroxide concentration, which lowers hydronium concentration, and the pH goes up as a result. How do we affect the pH by